Hi, my name's Jeff Hansen. I am a senior data engineer with ThinkBig Analytics, and today I'm going to talk to you a little bit about dimensionality reduction. So before we begin, I'm going to show a few examples just to give a basic idea of what it is we're talking about. If you look at this picture, who is this? Can you recognize who's in the picture? Similarly, what is this in the picture? Take a second to think about it. And finally, what about this? Hint, it's for kids. Some of you may get the reference. The idea I'm trying to demonstrate here is that some perspectives are better than others. In the case of that first picture, it's difficult to recognize somebody you may already know from the back of their head. Similarly, objects can be hard to tell what they are when you're looking at a bad view, the side of something, or just a bad projection. That's what we're talking about when we talk about projections. The view that you are seeing, so trying to get a better angle on things. And that's a lot of what dimensionality reduction is about, because in our day-to-day lives, we live in a three-dimensional world, and we're constantly looking at projections of three-dimensional objects onto two dimensions. Kind of like when you go to the movie and they project the image onto the screen. The screen's two dimensions, but you understand what you're seeing is really a three-dimensional representation of the world. So we are always going back and forth in our minds between 3 and 2 dimensions, and we're very good at this as humans. We have a little more difficulty when it comes to larger dimensions. So going back to those examples I showed, you can all probably recognize this now. That's Justin Timberlake. And this is an American quarter, 25 cents. And finally, for those of you who've seen the Hudsucker proxy, the circle was either a hula hoop or a straw. You may be thinking, great, but what does this have to do with machine learning? How can I use this to visualize my data? How can I use this to build recommender systems that recommend, say, products to new customers? And can this help me detect fraud? Yes, I'm not actually going to show you how to do all those things, but by the end, maybe you'll have an idea of where it fits in with many of these problems that we face in the world with big data. So dimensions in data. We just talked about those pictures of three-dimensional objects, but data goes beyond 3 dimensions. Those were more examples just to kind of understand intuitively what it is we're talking about. Now we're going to expand and go into many and many dimensions. What does it we mean, though, when we talk about dimensions in data? So with data, you know we have samples, and samples have variables. Samples are basically things. Items, objects, people. Things have numerous features, characteristics, attributes, variables, also known as dimensions. So when we talk about things and their variables, their attributes, we're talking about dimensions of those items, those objects. For example, if we're talking about documents or web pages, documents, web pages, they all have words, links, or authors. So the item or the sample would be a web page. The features or the dimensions of that web page would be words, all the words that show up in it. Links, authors. If we talk about words, let's say you have the word math. Math may appear 10 times in the document. You could consider math to be a dimension and 10 to be the value of that dimension. Similarly, images have pixels. They also have tags, maybe, if you're looking on some social networking site and people are tagging the images. Customers. If you're dealing with customers, you might be looking at the items that they purchase, their personal details, demographic information, maybe even their friends or social network graph. These can all be considered features, attributes, or dimensions of your customers. And finally, with financial securities, you may be looking at the price of an instrument, the volume of trades that took place during a given day, or the change in price over an interval of time. So why is it we keep talking about these as dimensions? Frequently with data, and you may be used to seeing them as a comma-separated file or an Excel spreadsheet or a database where you have rows and columns. Again, going back to that whole sample variable analogy, a row would be a sample, an item, and a column is generally a dimension or a feature. The reason we think of these sometimes as dimensions is because what we generally care about is the similarity between 2 different items. So if you have 2 rows in a database and you want to know how similar those rows are, or how similar 2 people are, if we treat each of the columns or each of the features as a dimension, then similarity just becomes an exercise in measuring distance between 2 points in space. So you end up with this multi-dimensional space, kind of like we went back with the 2 or 3 dimensions. And points which are closer are similar. So people who have more features in common are similar. People who have less features in common are more different. Let's take an example again. Suppose we have 2 dimensions in this case. We have an R user group and a Hadoop user group. And Claudia, John, Andreas, and Sonu are all members of both of these user groups. These are online user groups, and suppose we're just measuring how many times each of these individuals has posted a discussion item over the last month, say. So in the R user group, we have Claudia, who posted 8 different discussion items, and she only posted 2 to the Hadoop user group. Meanwhile, John posted 7 discussion items to the R user group and 7 to the Hadoop user group. Andreas and Sonu both posted, looks like 9 discussion items to the Hadoop user group, while Andreas only posted 5 and Sonu only posted 3 to the R user group. So looking at these people, if we plot them in this 2-dimensional space, you can see that Claudia and John have more in common than Claudia and, say, Sonu. Sonu and Andreas are pretty close, so they're pretty similar. You have something maybe even like a cluster over here, you could say. John, Andreas, and Sonu have a lot in common, and Claudia is a little bit of an outlier. So we're basically using distance between the 2 points in the space to measure similarity. When we talk about measures of distance, you hear various math-sounding terms, and I'm not going to go too much into these, but Euclidean distance, maximum distance, Manhattan distance, L-norm distance, these all sound a bit intimidating, and that's the general reason that I wanted to talk about this topic in the first place. A lot of the concepts that have to do with dimensionality reduction have these scary math-sounding terms, and I wanted to demystify them and make it more clear to people who have been maybe intimidated by the topic that it doesn't have to be that scary. The concepts aren't that complicated. It's just that they have scary-sounding names. So I'm not going to talk too much about the different measurements of distance. We're going to just concentrate on Euclidean distance in this case, which is, again, one of those scary-sounding terms for the length of a line between 2 points, just a straight line. So if you remember high school algebra or high school geometry, you may remember the hypotenuse of a triangle is the square root of x squared plus y squared. That's pretty much what we're talking about with Euclidean distance, and that's in 2 dimensions. If you were to have a triangle that had, if you're trying to measure the point between, or the distance of a line between 2 points in 3 dimensions, it would be x squared plus y squared plus z squared. If you're doing it in 4 dimensions, it would be x squared plus y squared plus z squared plus w squared, whatever your 4th dimension is. And you take the square root of that value, and that's the length of the line between those 2 points. Where, again, x squared is kind of the side of the triangle, but it's not so much a triangle anymore. It's the distance between x1 and x2. So back here, if you're just subtracting, Claudia is 8, John is 7, y would be 1 on that triangle. And Claudia versus John on the Hadoop side would be 7 minus 2. So you have this triangle that's 1 by 5, 1 squared plus 5 squared. That gives you the distance between those two when you take the square root of it. So you think 2 dimensions is hard calculating these distances, hypotenuse squared. Imagine trying to do that on millions and millions of dimensions. When your data gets really big, really wide, when you have lots of features in your data set, calculating item similarity becomes more and more complicated. It takes longer and longer. So this is sometimes called the curse of dimensionality. Not only can you not fit the data in your memory, but it just takes too long to calculate. What do we do about this problem? And that's a large part about what this topic is. When we say reducing dimensionality or dimensionality reduction, we're talking about taking millions and millions of dimensions and trying to come up with a representation of the data which is similar in structure, which captures the same original characteristics of your main data set, but does it in a smaller size of data. And this is made possible largely based on a theorem that Johnson and Lindenstrauss came up with. The idea of the theorem is that the number of dimensions doesn't matter. It's the sample size that matters. if you have millions and millions of dimensions, you can always project those millions of dimensions onto a smaller number of dimensions and maintain the distance between all 2 points, all combinations of 2 points, so that you maintain the structure of your data. And the number of dimensions you need to do that has less to do with the original number of dimensions and more to do with the number of points. And their theorem was that the number of dimensions you need is on the order of log n the number of points. Again, this sounds very mathy. If we put it in English, all we're saying is every time you double the number of points, you only need to add a few more dimensions to capture the distance between those points. So if you needed, say, 50 dimensions to deal with 1,000,000 points, maybe you would need 51 dimensions to deal with 2,000,000 points. And if you go up to 4,000,000 points, you only need 52 dimensions. If you go up to 8,000,000 points, you only need 53. You can see each time you double the size of your data set, you're only adding 1 or 2 more dimensions you need to the structure. Huh? I know that sounds a little complicated, but it is worth repeating. So I'm going to say this one more time. The number of dimensions doesn't matter. If all you care about is item similarity, no matter how many dimensions you have, an infinite number of dimensions can be projected onto a lower number of dimensions based on the number of points. So it's not the dimensions, it's the number of points that matters. And even though it's the number of points that matters, like we said, it's that log n nature. So lots and lots of points can still be represented on a smaller number of dimensions. Let's look at this a little bit graphically. We're going to go back to 3 dimensions and 2-dimensional projections. Imagine you had 3 points in 3 dimensions. Here we've got the y-axis, the x-axis, and the z-axis. And we have a point that's at 4 on the y-axis, 4 on the x-axis, and 4 on the z-axis. You can see where with 3 points, you don't need 3 dimensions to maintain the perfect item similarity. These points are all equidistant. This is going to be an equilateral triangle. However, there is a difference between a good projection and a bad projection. This is an example of a bad projection because it makes it look like the point up here is further away from each of these 2 points. And like the blue point is closer to the red point. In reality, what we said is all of these points are equidistant. So this would be a good projection. This projection is maintaining item similarity exactly. Now, if you were to add more points, you can't always get it perfect. So if we had 4 points, you might be able to get a close representation, but if those 4 points aren't all on the same plane, you are going to introduce some error into the equation. When you get up to lots and lots of points, you can't do that in 2 dimensions. You can't even do it in 3 dimensions. But as you add more dimensions, you can capture a lot of points and maintain the approximate structure of the original data set. So that was the graphical representation. You may be wondering, what are these dimensions we're talking about? So we just projected that onto 2 dimensions. What is the meaning of those 2 dimensions? And really, if you're projecting an infinite number of dimensions, say onto 50 dimensions, what's the meaning of those 50 dimensions? Sometimes this is called feature extraction. The idea that you're capturing a number of data sets or a number of data points, features, and attributes in your data set. But what if there were underlying features, underlying pieces of information about your people, your items, your points that you're capturing that you're unable to record? So what if those underlying features explain some of the features that you are able to record? You could think of that with topics in documents. So suppose you're just measuring the words that are in documents. What if each of these documents was about a topic? You can imagine that a topic of, say, science or math would be more likely to have certain words like singular value decomposition than topics about popular movies. So the topic, which we're not capturing in our sample set, there is an underlying topic which is explaining the appearance of a lot of these variables. And what you end up finding is that these underlying dimensions that you project onto, frequently they have a lot to do with something like an underlying variable, a topic. And frequently they call it topic analysis when you perform this on documents. The idea that you're capturing millions and millions of words, Instead, what you're doing is you're categorizing the documents on these more abstract dimensions, where the dimensions are something like topic. But this is kind of key. The features that we're extracting, as much as they may be like a topic, they might be like a genre, they're not so easy to quantify. And we'll see that with an example later on. But they have some kind of abstract meaning, and when you see the example, you get a feel for what the topic might be, but it's not a concrete topic that you could really put a name on. Now, you're thinking that sounds great, but how do I do it? So, unfortunately, dimensionality reduction frequently comes with a lot of different techniques that have, once again, scary math-sounding names. They all seem to have three-letter acronyms, so you've got SVD for singular value decomposition, pCA for principal component analysis, LSA for latent semantic analysis, LDA for linear discriminant analysis, and then we go off the three-letter acronym side and we get random projections and MinHash, things like that. There's a lot of different techniques. I'm going to talk about two of them in this talk, and I'm just going to give a basic overview. I'm going to talk about singular value decomposition and random projections a little bit later after that. Fortunately, pCA and LSA happen to be using singular value decomposition as the math under the covers. They just are different domains that came up with this concept, and because they were either unaware of SVD or they wanted to give it something that sounded a nicer sounding name within their domain, they came up with these new names. So latent semantic analysis is also called topic analysis. That's the one I was talking about, where you find the topics within documents. pCA is more a generalized process for just trying to find the variables, extracting the features that explain your data set. Before I do that, I'm going to need to take a step back and give a brief refresher of linear algebra. So don't panic. This is a bit of a crash course. For those of you who already know linear algebra, some of this will be very easy, and hopefully it might give a new novel approach to explaining some of the things that will help you have a more intuitive understanding. For those of you who haven't really done this before, I'm going to try to keep it somewhat simple so that you get a general idea, and this will give us a basis for understanding the topics like singular value decomposition. So before I go any further, I want to talk about vectors and projections. We've mentioned these a little bit, but suppose we have a point in space. Just like in those examples, we had the four people on 2 dimensions. In this case, we're looking at a picture of 3 dimensions. So A is a vector. A vector just means a point in space, really. So this point up here at the top of the arrow is the location of that point, and this is the vector pointing to that point. When we talk about projections, you could be projecting this vector A onto any other vector. And frequently what we do is we choose a unit vector. Unit vector just means a vector of length 1. So the standard basis vectors are generally the vectors of unit length 1, which reside on your axes. So z-axis has the k unit vector, the x-axis has the I unit vector, and the y-axis in this case has the j unit vector. Each of these is a vector of length 1. You don't have to use vectors that are sitting on the axes, though. We could have a unit vector like k, which pointed out in this direction. And when we talk about projections, what we mean is we take this vector a. If we project a onto the z-axis, all we really have to do is say the dot product of a times the vector k. And I'm going to show that real quickly in a slide. But dot products are what we use to project one vector onto another vector. And like I said, the vectors don't have to be, if they're unit vectors, it works great, but they don't have to exactly be on the axis. So these unit vectors, as long as they're orthogonal, which means perpendicular, as you can see, I is perpendicular to k and j, perpendicular vectors form a basis for an n-dimensional space. If you have n perpendicular vectors, you can use that as the axes of an n-dimensional space. Now, when we talk about vector dot product, that just means if you have vector A and vector B, the A dot B is going to be A1 times B1 plus A2 times B2 plus A3 times B3. And in this case, that might mean the x-axis of A times the x-axis of B plus the x-axis, or the y-axis of A times the y-axis of B plus the z-axis of A times the z-axis of B. But in these vectors, you're going to have a number of dimensions of them. You just take the similar dimension, multiply it, and then add up all of these. The other way to look at this is that it's the length of A, or the magnitude of A, times the magnitude of B times the cosine of theta. I'm sorry to be getting so math-oriented here, but the reason I'm giving this as a background is if B is a unit vector, which, like those I, J, and K vectors, if it has a length of 1, then the result is simply the length of A projected onto that line. So think of the vector dot product as an operation for projecting one vector of who knows what length onto another vector. And if that other vector happens to be unit length, the projection is just going to be the length of the original line, the original vector, on the line formed by that unit vector. So again, we talked about good perspectives or good projections and bad projections. Remember that a good projection is going to be one where the angle is so close to 0 so that the cosine of theta is 1. In that case, the dot product of A times B is just going to be the length of A. So if we had, say, the x and y axis, and we formed a plane, and we wanted to project the image of an object onto that plane, then we're talking about, in the case of the face of the coin, if the plane is parallel to the face of the coin, then if each of the points on the face of the coin was say a vector, and you were trying to find the projection of that coin onto a surface, the best surface is one that's parallel. The angle between the face of the coin and the surface of the plane they're projecting is 0. So that's a good projection. That's kind of what we talk about in this case. That's what we're looking for. Finding good perspectives to project our data onto, as opposed to bad projections where the angle is close to 0 or is close to 1, so that if it's perpendicular, you really don't get any added value. Now, beyond dot products, we're going to talk about matrix multiplication, which is commonly used for doing these projection operations. Think of A as a matrix of row vectors. So if this row is a vector, and this row is another vector, and this row is another vector, or similarly, if this is really your CSV file, this is a person, and this is a data point about that person, a variable or an attribute of that person, then you have a row vector that represents a person, and each dimension in that vector is just another feature of the person. So a matrix would then be multiple people, multiple rows. And if you want to project that onto a different space, you would multiply it by a projection matrix where each column has the same number of variables as each row in the first one. And each of these columns is a projection. It forms a projection vector. So B projects A onto C. And this is typically how people that I've talked to think about matrix multiplication. I'm going to let you in on a little secret. Personally, I've always struggled with matrix multiplication because order matters. You can't just take A and B and say B times A is equal to A times B. You have to get in the correct order in the first place. And for me, this has been difficult. I think probably because I never did my homework as a kid. But if you've done the exercises so many times, this just becomes simple. If you haven't, I have a trick that I like to think of that makes it easier for doing the multiplication. So again, going back to vector multiplication, you can see C1 is going to be A1 times B1 plus A12 times B21 plus A13 times B31. That's shown up here. And each cell in this resulting matrix is going to be similarly the dot product of the corresponding row and column from this matrix. But if you're not familiar with this, if you haven't done it that many times, how do you remember the size of the output? So you have these two matrices, you're multiplying them together. I always have trouble remembering how big is this output matrix going to be. Or have I put these in the right order? And I think it's a little bit easier if you think of it a different way. So I'm going to show a little visualization real quick. If we start with this times this, rather than looking at it like this, I like to shift up the matrix on the right side of the multiplication and shift over the one on the left side. And then it's very easy to see that the result is now a 4 by 5 matrix. So if you have a 4 by 3 times a 3 by 5, this is the correct result. If this matrix and this matrix had been in the wrong order, you would also see, if you form a cube by this, that the number of rows wouldn't match up with the number of columns. So if these two aren't if you can't multiply them together, you wouldn't form a cube. Personally, I find this way of visualizing the multiplication an easier way of remembering how to put the things together. So just remember, make a little cube, and then any one of these points when you want to multiply, it's just the corresponding row times the corresponding column. One of the reasons I like the cubic view is because you can think of the multiplication as being the column, or the row times the column, which is the projection. This is B projecting A onto your new space of C. But also, you could think of it more as a layered view, where instead you say that it's the row, or the column times the row, plus the column times the row, plus the column times the row, equals the full matrix. So in this case, this field would be A41 times B11, and so on. So you end up forming 3 full matrices, and then when you add the totals up, which means that you add this field to this field to this field to get the first field, each of these layers is a separate operation to building a complete field. One of the reasons that I like that is because this cubic view helps you figure out where to break up the operation. So let's say you wanted to write a parallel, you wanted to distribute the workload to multiple subprocesses. You're writing an algorithm, a computer program to do this. When you look at the cubic view, it's very clear that this column of B needs to be sent to the first quarter of the first subprocess, but also the third subprocess. Similarly, the first row of A needs to be sent to this subprocess, but also this subprocess. So each column of B needs to be sent to 2 or more subprocesses, and each row of A needs to be sent to 2 or more, but not the same subprocesses of the operation. On the other hand, if you broke it up in the layered view that I described, you can just take the first column of A and the first row of B and send that to one subprocess. Then you take the second column of A and the second row of B, and you send that to a different subprocess. And the third row of A, or third column of A, and third row of B, and send that to the last subprocess. And in this case, you only need to send them to one subprocess. So if anybody's ever worked with MapReduce, you can see where this would be a very easy mapping operation. This is another very easy mapping operation. This is another easy, so 1, 2, 3 mappers come up with 3 complete views of the matrix. And then you reduce them by adding up each of the individual cells to get the final output. So I just find this to be a useful way of viewing the operation for then understanding how to break up, or how you can break up the math. Beyond that, this is all fine and dandy, but why are we looking at this? And what if you could break up, what if you could reverse the operation to factor a matrix? So rather than coming up with A times B equals C, what if you had C to begin with, and you wanted to find matrices A and B that multiplied together gave you C? You can. This is called matrix decomposition. And again, we have a number of scary sounding math names like LU decomposition, QR decomposition, eigenvalue decomposition, and singular value decomposition. Again, like I said, we're going to talk about singular value decomposition, but these are other forms of just decomposing a matrix or factoring it into two or more submatrices that, when multiplied together, give you the original output. You're probably wondering, why might you want to do that? Think of our data. Imagine instead of having that multiple matrix, which was 4 by 5, instead imagine it was 1 million by 1 million. So suppose you had 1 million people and 1 million movies. How many combinations of people and movies would you have? That would be 1 quadrillion, I believe. 1,000, million, billion, trillion. So that would be 1 trillion, sorry. Instead, what if you had two matrices, A and B, that when multiplied together gave you this output C, where A was only 100 by 1 million and B was 100 by 1 million, or rather 1 million by 100 and 100 by 1 million. Again, I told you I'm never very good at remembering which direction the dimensions have to be. So the total number of cells in that, the total data size of that representation is only 200 million. Rather than 1 trillion, you only need to store 200 million fields. It's a much smaller representation. And we can use that. That's something that you could probably compute on your computer rather than needing a huge cluster to deal with. So again, imagine C is a matrix of people who have watched movies, and every row represents a person, every column represents a movie. If we can find a matrices A and B where A times B approximate C, then we would have this model of A where each row of A models a person, and the distance between two rows of A model relative similarity. Each column of B models a movie, and the distance between two columns of B model the relative similarity of movies. So in this case, if A times B equaled C, imagine trying to calculate the distance between two rows of A, where you have to say the distance between A1 and A2 and B, or A12 and A122 and A13 and A133. So the distance between this vector and this vector is much easier to calculate than the distance between this whole set of million values and this other set of million values. You only have to deal with 3 dimensions, or in the case we gave 100 dimensions, rather than a million dimensions. So the computation is much faster, the space required is much smaller, but if you multiply this model of people times the model of movies, you get your original vector back, or your original matrix, your original data set back. In this case, you may have a huge data set that you store in a big cluster, kind of like a dupe, but you can do the computation. You can work with your data because you have the same structure down on a laptop, or even just a large instance that's hosting R or something. So it's easier to not run parallel operations where you just play around with your data a little bit, visualize it, and then after you've formulated your hypotheses, you can go back to the original data set and test them on that. So how do you do it? And this is where one of the operations, singular value decomposition, comes in. Singular value decomposition doesn't give us A times B equals C. Instead, if we have a matrix A, we end up decomposing it into 3 matrices. So U times sigma times V star. And U and V have these special properties, and sigma is another special property type matrix. U and V are both square orthonormal matrices. That's a big sounding word. All that means is that every row and column of U and V is a unit vector. So unit vector means, remember, A squared plus B squared plus C squared plus D squared plus E squared plus F squared. All of those individual values, all those cells, the dimensions of U, any vector in U, add up to 1. So the square root of the sum of the squares adds up to 1, and 1 squared is obviously still 1. So the sum of the squares of all the values in any row or column of U and V is going to be equal to 1. Also, beyond that, because we say orthonormal, that means that each of these vectors is perpendicular to one another. So if U is a 5 by 5 vector, or 5 by 5 matrix, each of the rows and each of the columns of U is perpendicular to every other row or column. So if you multiply any of those together, if you multiply, since they're all of unit length 1, if you multiply one vector by itself, you're going to get 1. If you multiply that one vector by any other vector that's perpendicular to it, you're always going to get 0, because it's going to be the length of the first one times the length of the second one times the cosine of theta. If the angle between them, if they're perpendicular, it's always going to be 0. If they're parallel, if it's the same vector, it's always going to be 1. Which gives you some nice qualities of these, because if you multiply V star times V, you get the identity matrix, which is a diagonal matrix of all ones going down the center, going down the diagonal, and the rest of them are 0. That means you can take V and multiply it by V star, or V star and multiply it by V, and anything you multiply that by that gives you the same thing. So U times sigma times V star times V is the same thing as U times sigma. And we use that a little bit to simplify a number of the operations we do. So what's the sigma vector I talk about? It's a rectangular vector, because remember, U is going to be, if A is rectangular, U is going to be a square vector that has the number of rows and columns equal to the number of rows in A. V is going to have the number of columns in A. Sigma is pretty much a rectangular matrix that lets you multiply U times V, since U times V don't have compatible sizes. And we'll see this graphically in a second. But sigma is also a diagonal matrix, where all it's really doing is multiplying each one of the columns of this by one value on the diagonal. And I think it'll make a little more sense when we look at it graphically. The other part of sigma is that the values decay. They get smaller. So the first diagonal value, and let's jump over to a picture. If this is A, the resulting matrix, and this is U, you can see U has the same number of rows and columns as you have rows in A. V star has the same number of rows and columns, it's a square, and it has the same dimension as the columns of A. Sigma then is going to be just this rectangular one that allows you to multiply U times V. And I've showed all of the gray values here are zeros, so you can just ignore them. And it has diagonal values which decrease over time. So this is the largest value, this is the second largest value, this is the third largest value, and they get smaller and smaller as you go down the line. I apologize for the lack of pretty colors, but it'll get a little more colorful in a second again. So if we go over here and we look at this multiplication, remember how we said this times this is going to be shown as a cubic operation. When we do that, remember this is U, and each of these columns has unit length of 1. Meanwhile, each of these diagonal values has a decreasing value. So you can see that the first column of the result is going to be equal to the first column of U times that first singular value of sigma. The value of the second column of U times V, or U times sigma, is going to be equal to the second column of U times the second singular value, because these are all 0 and these are all 0. So if you take this and multiply it by this, you end up getting 0. And you can see all of the work is done in this one column times this value. All of the work is done in this one column times this one value. And that gives you this projection right here. So if these are all unit length of 1, each of these columns is unit length 1, you can see that each of the magnitudes of these columns is going to decrease. And the magnitude will be equal to the value of this scalar, this number, the singular value. That's why I show the results kind of shading over time. Now if we go to the next phase, so if we just fade away U and sigma, and we only look at U times sigma, and multiply that times V star, and I did it a little bit differently, but in this case you can see the highest significance, the single most important row and column, they get multiplied first. And then remembering that layered view, since you multiply this times this, you're going to get an approximation of the resulting matrix. Then if you multiply the next one, it essentially corrects for error. So the second layer has a smaller value. The magnitude of it is less because your singular value is decreasing over time as you go back. And each time you add another layer, you're essentially refining the result of A. So you're getting a better and better view of A. And personally, I like to just move those over and think of my singular value decomposition as being A equals U times sigma times V. And then I take that a step further, and I reorient everything so that I have A over here and U times sigma times V over here. And this makes it a little more clear that you can just kind of take away all of this light stuff because there's not a lot of value here. So if we want to reduce it, we want to shrink down our data size. Now we can just say, well, hang on to a couple columns of U, a couple columns of V, where this is actually V star. And then you've got your decreasing singular values over here. And when you multiply this times this times this, you get a near approximation of A. Again, any one of these, if you, oops, my bad. I'm going to go back over the slides. So in this case, we have U times sigma times V starred equals A. And if we ever want to reconstitute a cell of A, we just say that it's going to be this row, this vector, times this vector, times this vector, essentially. So that this cell is equal to this times this, plus this times this, plus this times this, times this. And as we go further on, we get a closer and closer value of this. If you keep all of the values, you get the exact value. If you just throw away half of this, then you get a close approximation. So in a really large data set, this would be a huge square matrix, and this would also be a huge square matrix. That doesn't solve our problem. We just want to approximate. We want to throw away the stuff that doesn't add value and have a smaller representation. But also, because of singular value decomposition, remember I said if you have A equals U times sigma times V star, but V star times V is just the identity matrix, then if you multiply both of these by V, you end up with A times V equals U times sigma. So the nice thing about this is suppose we have A, and we already know U times sigma, and we have V. What if we wanted to bootstrap a new customer? Suppose we get a new customer that comes to us and we have their history, and we want to put them into the model. So we calculated the entire model last night, but now we need to add a new user to it without recalculating the entire model. Well, we know how to do that because we have a new row here, and we just want to calculate this row over here. It's going to be equal to this times this, gives you this field. Then this times the second column of V gives you the second field. So this little submatrix is just equal to this matrix, a one row matrix, times the model for V. Right around now, you may be seeing double and wondering, what does it all mean? I think it might be helpful to look at a graphical representation again. So let's take an example of an image. Instead of looking at movies and people, we're going to say that each of the pixels of this image is a cell in our matrix. So this image is 321 by 480 pixels. And we're going to treat it as a matrix of grayscale pixels. We're going to run single value decomposition on the matrix, and then we're going to evaluate the singular values to the diagonal scaling matrix. We'll take a look at the decay that I talked about. We're going to recompose each of the individual layers, kind of like we talked about before, but I'm going to do it first one layer, then 2 layers, then 5 layers, then 10 layers, 20 layers, 50 layers, and then 100 layers to give you an idea of what it is that we're correcting for with error. Now, I'm also going to say ahead of time, an image is typically not what you do. You don't do this with images because we're treating this column as being something related to itself. But really, this pixel up here doesn't have a whole lot to do with this pixel down here. This is showing that even when there isn't a whole lot of connection between two cells in a column, that you can still use the generic purpose singular value decomposition to compress your image. So this isn't how people typically compress images. I'm just using it here to give a general idea and a more intuitive understanding of what it is that we're doing with SVD. So here's the decay of the singular values that we talked about. Remember that diagonal matrix? You see up here you have 300. So the first most important diagonal value is 300. And the second one drops all the way down to 50. So since this was a 380 wide matrix, you end up with 380 singular values. And you can see that they drop off rather quickly. Over here, somebody once asked, what is this significance? What is this axis representing? What does 300 mean? Well, it's kind of error. It's a little bit difficult to say, but you could say that if we go back to this, one of these visuals, and so if this is 300, and we say U times sigma equals V, I'm sorry, U times sigma times V star equals A, but also A equals U times, A times V equals U times sigma, going kind of forward to this one. If you think of U times sigma, and remember these decrease, so the magnitude of this is going to be, this whole vector is U times the first singular value. In that case, it was 300, whereas this is 1, because each of these columns in U is 1. So U times sigma, the first column is going to have a magnitude, a length of 300. The second is going to have a magnitude or length of 50. The third one is going to have a magnitude or length of the third value of that singular of sigma, basically. But what we're saying here is when you multiply A, the entire matrix of A, times the first column of V, which in this case I've shaded it, but remember V is also a unit vector. So these are all orthonormal unit vectors. So A, if you multiply A times this first column, which is of length 1, you end up with the output being of length 300. And if you multiply A times the second column of length 1, you get a result which has a length of 50. So this is really telling you the variance on this dimension. So this is, you're projecting A onto a dimension, and you're finding that all the points, the variance between all of the points on A when projected onto this dimension, have a variance of 300. If you project all of these points onto this dimension, you get a variance of 50. And I think that's kind of what principal component analysis talks about. Finding the dimensions of your original, finding the axes that give you the greatest variance of all of your points in A. So going back to this, the first singular vector gives you points, plots points onto an axis which has the greatest variance. And the best you can do is get a variance of 300. Then you can correct for error with a variance of 50. And then you correct for error with another variance of 50, and so on. And down here, when you project them on, it's kind of like looking at the side of the quarter. There's not a whole lot of variance going on here. This is capturing the most variance and showing you the best projection. This is the second best projection, the third best projection, and so on. So that, I don't know if that helps at all, but that's pretty much what these singular values are telling you. Now looking at them graphically, what is that first layer telling us? And you can see it's basically, is this column a light column or is it a dark column? What is the average essentially of all of the cells in this column? If it's light, you see a lot of light values. If it's dark, you see a lot of dark values. Similarly, the model for this row, is it a light row or is it a dark row? And then when you get the interaction of a really, really light row with a really, really light column, you see something very, very light. Whereas if you get the interaction of a very dark row with a very dark column, you see something that's very dark. That doesn't look much like the original image, though. If you add in 2 layers, the second layer essentially corrects for error. So you start with something light and dark, and then you subtract from it. And then you add 5 layers of correction in, and you get something closer to the original image, but still not really something we can understand. Now we go up to 10, 20, and 50 layers, and you can see the image starts to show up a little better. So now we can make out the image of a castle. Even here we can make it up, but it's pretty blocky. And finally, at 100 layers, out of 380 layers, you get something that looks pretty close to the original, where the original is over here. Again, like I said, you would not use this for compressing images. It's not the best approach. There are better approaches, but this is trying to demonstrate what it is that singular value decomposition is doing with the image. The downside of SVD is that it's computationally expensive, and not so much for small images, but when your data gets bigger, it doesn't scale well. It scales on the order of m times n squared. So imagine we have an n by n matrix. If you want to decompose it, the size of the data in that matrix is m by n, but we have n squared here because you actually have to do multiple passes. If you have 100 by, say you have 200 by 100, you would have to take your data size of the matrix is 200 by 100, but if you have to pass over that data 100 times, you're doing 200 by 100 by 100 computations. And this is what I mean by multiple passes. For every dimension you have in n, you still have to do another pass over the data. It also isn't easy to compute in parallel. There are ways of doing it, but there's certain tricks, and they don't always work well. They don't always parallelize. You end up with certain bottlenecks sometimes, and they're iterative approaches. So essentially, it doesn't scale well for big matrices. And in this case, we're generally worried about big data. That's why you've probably come to watch this movie. So what do we do? And the answer here is rolling the dice, essentially. Random projections, a little bit of randomness goes a long way. When we introduce a random variable, we can make the computation a lot simpler, a lot easier to parallelize. So going back to this relative similarity, if you don't necessarily care about reconstructing the original matrix A, remember singular value decomposition gives you that U times sigma times V equals A. But if we already have A and we don't care so much about reconstituting A, if we just want to project our data down onto less dimensions so that we have a model of A that models the rows or that models the columns, we don't even need to run SVD. Random projections are nearly as good. Instead of, say, using 50 dimensions, you may still have to add more dimensions in and use 60 or 70. But you don't have to use that many more, fortunately. And there's math that proves this. You can also often run this in a single pass. So when you do these random projections, it's very easy to just create a matrix of random values and multiply it by your original matrix and get your new model, your projection. But doing that matrix multiplication, you just run that once on your data. You don't have to do an iterative approach to find the answer. It's also easily parallelizable, because remember, we're just talking about matrix multiplication here. We have a random matrix and we have our original matrix. So we already showed how you can distribute that by looking at that cubic view. All you're doing is taking 2 matrices and multiplying them together. And it's important to understand that the dimensions are not any longer ordered by significance. So we don't get that singular value, the middle matrix. Instead, we're just taking the original and the output, or the random, and getting a model that gives us, that represents the structure of our data set in 50 or 60 dimensions, or however many dimensions you choose to project it onto. On the other hand, you can actually use this to calculate a fast approximation of SVD, and I'm going to do that in a second with our last example here. The simplest approach to doing this, and I'm not going to go into the details, but there is a paper that you can reference. You create a random projection matrix from normally distributed values. So essentially, if you think of we talked about B, when you do A times B equals C, where B is a projection matrix, and each of the columns of B is a unit vector. It doesn't have to be a unit vector, as long as the length is always the same. So if we have 1,000,000 dimensions and we want to project them onto 50 dimensions, we just need a matrix which has 50 unit vectors, or 50 vectors which are all the same length, so that when you multiply, if you project onto them, and each of these is 1,000,000 long, if you just take a random uniform variable and make that be the vector, so if the vector is just a bunch of random uniform variables, the length will get longer and longer the more variables you have in there, but you don't need to normalize it for a unit vector, because if all of the vectors are on average the same length, then you get a decently uniform random projection. The other side, when you have lots and lots of dimensions, it's actually very easy to come up with perpendicular. We talk about needing an orthonormal basis. Forget about the normal. They don't have to be unit length, like I just said, but we want vectors that are perpendicular. And when you take 50 vectors out of 1,000,000 dimensions, the odds are very low that any of those are going to be close to parallel. So you will generally end up with very, very perpendicular matrices or vectors. So as an example, I took the Movielens Dataset, which is 10 million movie ratings. It's 10,000 movies, 72,000 users rating 10,000 movies. I imported that into R as a sparse matrix. I threw away the actual ratings. So if users rated movies 1, 2, 3, or 5 on a 5-point scale, I don't care about the rating. I just said, did they watch the movie? If a user rated a movie, that means they watched the movie. If they watched the movie, there's probably a reason they wanted to watch the movie. So whether they liked it or not, they had a reason for watching it. That reason may have been they went on a date, so they didn't really want to watch it, but because of their lifestyle, they had to go with somebody else who wanted to watch it. Maybe they have kids, but for the most part, people watch movies that they think they're going to like. It doesn't matter if they actually like them. It's better to know if they thought they might like it. At least that was the logic I was using in this case. And because we have lots of empty columns, the matrix is actually 72,000 by 65,000. The way that this data set has movies, they must have had more than 10,000 movies and just cut it down to the 10,000 most rated movies. So we have a lot of empty dimensions here. And one thing that this shows is that random projections can actually handle empty dimensions very well. So rather than having to come up with consistent numbers or a dense matrix where you only have 10,000 columns, it's okay to say we have a sparse matrix that's 65,000 columns wide, even though 55,000 of those columns are empty. And I just used R and a sparse SVD based on a random projections, which I took straight from some code that Ted Dunning added to a Stack Overflow. He actually one time when I was talking to him, he mentioned this process, and at the time I thought I have no idea what you're talking about. I'm going to have to go look into this a little closer, but now I understand it. And if you want to understand it better, he references a paper that explains why this is possible. I highly recommend reading it, but it is about a 72-page read, so it'll take a little while. Anyways, thanks to Ted Dunning for this approach, or for the code, and thank you for the writers of the paper for a really good read. So when I took the data set, in this case, looking again at the decay of the singular values, I used that random projection and then projected randomly onto 60 dimensions, took those 60 dimensions and then re-ran singular SVD on that new matrix to find an approximation of the singular values and an approximation of the best singular vectors. Then I took the first 4 of these and I just plotted them. So dimensions 1 and 2, if this is dimension 1, remember from the picture what we found, typically the first dimension is just telling you, is this a dark column or a light column, a dark row or a light row? In this case, I'm not looking at the users, I'm looking at the movies. But is the first dimension is generally telling you, is this a movie that got watched a lot, or is this a movie that never got watched? And because of all those empty columns, you'll find that most of the movies that never got watched, that show up all the way over on this side, they don't have titles because they're just sparse rows or sparse columns. Whereas over here, the movies that get watched the most are just going to be your blockbuster hits. And it's not so easy to see these, but also you don't necessarily find that much of interest. It's not that surprising that really big blockbuster hits are the ones that show up over here. What you do find though on dimension 2 is some of that error correction. So if you look up here, you may see movies that have something in common. And like I said, this dimension, it's kind of that topic analysis, but you can kind of see people who watch these movies, because this is based on collaborative filtering, are less likely to watch these movies. And there's something about these movies that's different from these movies, but it's not really easy to quite put it into words. Similarly, if we look at dimensions 3 and 4, you have movies over here on dimension 3 that are different from movies over here, and there's a whole lot of movies in the middle. What I'm doing is plotting only the bottom 20 and the top 20 on each dimension, because otherwise we would just see thousands and thousands of titles overlapping here. And you can also see a lot of these bundle up over here, whereas down on the other side there's less bundling. So some of these dimensions, while the error correction may be more on one side than on the other side. And just to get an idea, if we look at dimension 1, like I said, movies you've probably never heard of, I went and I found the first 10 or 15 that actually had titles, versus blockbuster hits. And then dimension 4, all the way on the one side, maybe you'd consider these movies with some type of substance versus fluff. You get a feel for some meaning that this dimension adds, but it's very abstract. And for today, I'm afraid that's all I really have. I'm hoping I will be able to get some of that code, if anybody's interested, the code that produced both the image and the random projections of the movies, up on our blog. Feel free to email and ask if I don't have that. Or if you do have any questions, feel free to email our Think Big and ask, and I'll be happy to respond, or maybe write up a blog on responses to questions. Thank you very much for your time, and have a great day.